Hello, today we'll be looking at the US steel column calculator in ClearCalcs. So here we have different presets, but we'll use the generic concentrally loaded column. We are designing in AISC 36016 ASD, and the assumptions are stated here. So in our calculator, we have various member cross-sections available. For example, you could have a C-channel, and all of the member properties can be viewed here if you open up the designation tab. We have options for continuous bracing. So if you were to select yes for X-axis buckling, it would disable all of the strong axis buckling checks in compression, and it would consider the column as braced. Normally, it is conservative to assume that the column is not braced, so by default, we'll have all of these set to no. The supports in this table here are measured from the bottom of the column. So if we were to put a roller support at a distance of L/3, we can see that our dynamic diagram now updates and we'll have a roller support 1/3 from the base. Our default load eccentricity can be set, and this will be applied to all of the axial loads in the table. Should you want to change this value for one load specifically, you can input that in the individual load in the table. You can also link your column to another sheet you created. So for example, if you wanted to link this to the reactions from a beam you made in ClearCalcs, you can do so with this link button here. You also have the option to apply weak axis loads. So this would be loads that are applied about the y-axis. The inputs are similar to those that are found in the strong axis loads. In our capacity and pure axial loading section, you can find that we have override factors. So by default, for the effective length factor K, it is set to equal 2 for cantilevers or 1 for other spans, as this is conservative in most situations. But if you were to have different scenarios where you might want to use a recommended design value of 0.65 for this example here, you can do so by overriding that in one of these boxes. We also calculate the buckling strength, which for slender sections is reduced to account for the effects of local buckling, and this is based on the effective area, AE instead of A, for slender sections. So if we were to scroll back to our summary, we can see that our design is governed by the compressive strength. If we were to include a weak axis load, however, let's go and put one in. Let's just use a dead load of 10 pounds. We can see that all of the calculations that we need to consider will now appear, and this would include things like flexural strength, or the interaction between compression and bending, or deflection.